let's finish up this arc length example where we're integrating with respect to y. So I mentioned the fact that we have to get a common denominator here and simplify. So this 1/4 is really the same as all of this over 4, and so really I just need this to also have a common denominator of 4. So that'll give me the square root of 4, because remember this is 4 over 4, plus e to the negative 2y minus 2 plus e to the 2y all over 4. Notice here that I've got two constants that can be combined. Also, I'm square rooting the top and the bottom, and the bottom is a perfect square, so I'm going to pull that out. So my numerator is still square rooted at this point, but remember 4 and negative 2 can combine. So I've got e to the negative 2y plus e to the 2y plus 2 all divided by 2. Alright, so I just square rooted that 4 and made it a 2. Okay, from here we need to get a little bit creative. It turns out that this top expression here we can actually simplify, and that's going to allow us to do some really creative factoring. And so I do feel that this is the part, or at least one of the parts, that the book completely glazes over and expects that you totally understand what's going on, and I don't think it's obvious at all. So first of all, this 2 on the bottom is no longer in the square root, and so it's really just a 1/2 constant multiple which can be pulled outside of your integral. And so now I have all of this inside stuff being square rooted, but I want to think of it like this. This negative exponent is kind of in the way right now, so that can be written as 1 over e to the 2y plus e to the 2y plus 2. And the thing is that I really need to get a common denominator between these three terms in order to add these fractions and once again do that square rooting. So if I can, I'd like to just work outside of the integration for a minute, because it's going to be a while before we can actually integrate any of this. So I just want to focus on getting a common denominator between these three terms. So the common denominator is obviously e to the 2y, and the first term doesn't need to be multiplied by anything. The second term needs to be multiplied by another e to the 2y, which makes an e to the 4y. The third term also needs to be multiplied by an e to the 2y. So 2e to the 2y. And again, the purpose was to get a common denominator, so don't forget to write that common denominator. So what I have is this integral where I'm square rooting this fraction. And just like we did before, we can square root the top and bottom separately. Where the bottom is a perfect square. If we square root e to the 2y, then it pulls out of the square root and just becomes e to the y. So that's not a constant multiple. I can't just pull it out with the 1/2, but it's going to help. I need to switch my paper again. So let's continue working through simplifying all of this. So we're here, and that square root expression, that really ugly square root expression, can actually be factored. So I'm going to do that. I'm going to factor that. And and then I'm getting closer to being able to integrate. I forgot my dy when I wrote up here. So once again, let's just pull that expression off to the side. Whoops. And work with it. Try to factor it, and then we'll put it back in once it's factored. Now this is something that comes up a lot this week in this section, this really crazy factoring, where you're factoring things that aren't exactly quadratic, but they're in quadratic form. And so what you're seeing here is that the exponent here is double the exponent here. So that makes it a really good candidate for this quadratic factoring. And one of the videos that I posted this week was a YouTube video from another instructor that talked about basically how you would approach that strategy. It is something that I know is taught in a college algebra course, but it's probably been forever since any of you have taken one of those, and you're just a little out of practice. So anyway, it might be nice to do sort of a substitution here. And if I let my x term be e to the 2y, then what's going to happen is that this whole term is really just going to become a 2x, and then a plus 1. And then this term right here, e to the 4y, is equivalent to e to the 2y squared, or in terms of x, that's really just x squared. So if we think about the factoring of this quadratic, it factors into x plus 1 times x plus 1, or in other words, x plus 1 squared. So I can't go just introducing an x and throw that back into this integral, but we need to resubstitute. So remember that x was the same as e to the 2y. So really the factored form is e to the 2y plus 1 quantity squared. And so I'm going to plug that back into my integral. Hopefully you can see why that's helpful. I've got a perfect square, and anytime I have a perfect square, I can square root it. Now I know what you're thinking, we haven't even integrated yet, this is exhausting. But you'll see that a lot in Calc 2. We've just got problems that we're bringing in every facet of mathematics that we've learned. And that's kind of the point, you know, let's bring everything together. It's a building block of, you know, just putting all of your mathematical knowledge together. So anyway, the square and the square root cancel each other out. And I'm left with this fraction. Okay. Now, once again, I don't really love the fraction when I'm integrating. So what I can do is I can divide each term by e to the y so that the fraction can go away. So if I take e to the 2y and divide it by e to the y, I'll get an e to the y. And then if I take 1 and divide it by e to the y, I'll get e to the negative y. So essentially, when the book shows this problem, it goes all the way from the point where we squared our g of y function, and then it just jumps right down to here and says, obviously, that simplifies to this. And it's really not obvious. We had to do a lot of really crazy work with the fractions and the common denominators, and then all of this factoring. So hopefully you can get a little better understanding of where all that's coming from. We're ready to integrate. And excitingly, this is not a difficult one to integrate. We don't have to use any u substitutions, anything in terms of e to the x or e to the y. It's pretty easy to integrate. So first of all, I've got a 1/2. Don't forget to pull that out front. And then let's integrate each term in our expression with respect to y, and then of course evaluate it over the interval. E to the y integrated just gives me e to the y, and then e to the negative y will give me negative e to the negative y. Alright, now let's plug the natural log of the square root of 2 plus 1 in. This gets tough again. There's a lot of really careful algebra that needs to occur. So I'm going to leave that 1/2 out of it for now. And then I'm going to have e to the natural log of the square root of 2 plus 1 minus e to the negative natural log of the square root of 2 plus 1. From that, I'm going to subtract. I should put an extra set of parentheses around these things. From that, I'm going to subtract e to the 0 minus e to the negative 0 when there's no such thing, so it's just 0. Simplifying, when you take a base and raise it to a power where you've got an e and a natural log, those actually cancel each other out and all you're left with is the argument. So in that term, I have just the argument square root of 2 plus 1. Next term is tricky. Remember with logarithms that if you have a constant multiple, it's really the power. So this is really e and natural log being canceled out, but then it's the square root of 2 plus 1 to the negative 1 power. So minus the square root of 2 plus 1 to the negative 1 power. Again, I'll put extra parentheses around all of that. This is going to be nice here. E to the 0 is 1. Subtract another e to the 0, 1, and so you get 0. Alright, more fraction work to be done. I need to take these two expressions and I need to combine them. And the way that you're going to see that happening is by getting a common denominator, because this is really 1 over the square root of 2 plus 1. So let's go ahead and get that common denominator. We're going to multiply this term by the square root of 2 plus 1. Remember that we're multiplying by the square root of 2 plus 1 on the top and on the bottom. And when we multiply on the top, we have to FOIL. So the square root of 2 times the square root of 2 is 2, plus root 2 and another root 2, so that's 2 root 2 plus 1. This one already has the common denominator, so I don't need to multiply it by anything, so I'll go ahead and add that negative 1 in with that numerator and write the entire fraction over the square root of 2 plus 1. Keeping it moving, combine some like terms within the numerator. 2 plus 1 is 3, 3 minus 1 is 2. So 2 plus 2 root 2 all over the square root of 2 plus 1. At this point, I can factor in my 1/2, and really what that's going to do is just going to cancel the 2's on the top. So I'm going to have 1 plus the square root of 2 over the square root of 2 plus 1. And this actually can be simplified even further by multiplying top and bottom by the conjugate of the denominator. This, again, really tricky, something that's not obvious at all, but it's just called rationalizing the denominator. Let's get rid of the square root from the denominator by multiplying on the top and on the bottom. And when you do, you're going to have to FOIL both the top and the bottom. And so you're going to get the square root of 2 minus 1 plus 2 minus the square root of 2. Whoops, sorry about that. I'm going to run out of time here, but do all of your simplifying. Hopefully you're going to get an answer of 1 after all of this. The answer comes out to be 1.